coupling constant in NMR spectroscopy. To go with this topic, let us consider this example again, in which we have seen that for this proton it is getting quartet signal and for this proton it is getting doublet signal. Now if you observe this signal carefully, then there comes a separation between these two peaks with a constant value, it is given by J, and similarly for this doublet signal the separation between these two peaks it is given by J, which is called coupling constant. Thus the separation of multiplet lines of NMR signal in the unit of hertz, it is known as coupling constant. Now the coupling constant has notation which is given as like this, in which n, j, x, y, where this n it represents the number of bond between the non-equivalent proton giving the NMR signal, and x here it represents the proton that is giving the NMR signal, and y it represents the proton that is responsible for coupling. To understand this notation for coupling constant in better way, let us consider this example, in which here Cl, Cs2, Cs3, it is of p type of proton and it is of a type of proton. Now if you observe this molecule, then it looks like this, in which from B to A there is 3 bond distance. So we can give the signal as 2 proton of B types will give quartet signal, that is this proton that will give quartet signal, and its coupling constant it is represented by N, that is 3 bond, 1, 2, 3 bond from B to A. So 3 J, it is the signal for B type of proton, so B type of proton due to coupling with A types of proton. Likewise for 3 proton of A types it is given as triplet signal. Here it will couple with this one, that is a B type of proton. Thus the coupling constant will be given by 3J A types of proton coupling with B types of proton. So 3 protons of A type triplet 3JAB. Likewise, to get into more details for this topic, we will consider this example with the problem in which it is said that in proton NMR spectrum of organic compound which is recorded on a 300 MHz instrument, a proton resonates as a quartet at 4.20 ppm. The individual signal appear at that is delta 4.17, 4.19, 4.21 and 4.23 ppm. The coupling constant J in hertz is given as. So for this question we can consider the figure as like this, in which the quartet signal it is given as 4.17, 4.19, 4.21, 4.23. So there each peaks having the values in the NMR scale. Now as we have seen that the separation between these two peaks it will give the value of J, that is coupling constant. Now if we subtract between these two peaks, that is 4.19 minus 4.17, then we'll get the value 0.02 ppm. So that is the value of coupling constant in ppm. Now to get it in hertz, since we know that for 300 MHz instrument 1 ppm means it is 300 hertz. That we already discussed previously, that taking 100 MHz instrument in which 1 ppm it means that 100 hertz. Similarly for 300 MHz instrument 1 ppm means 300 hertz. Likewise if it is 1 ppm which gives 300 Hz, then for 0.02 ppm it will be 0.02 ppm into 300 Hz. So they will give the value 6 Hz as a value of coupling constant J. Coming towards the unit of coupling constant, in which standard unit of coupling constant is Hz. Since ppm is non-standard unit, as for J value, Hz, it is independent of B naught, that is applied magnetic field, but for ppm it is dependent of B naught, thus Hz is standard unit. Now the coupling or splitting of NMR signal is through bond process, and as the number of bond increases, the value of coupling efficiency decreases. With that, we will see this notations as here 1J, it is one bond coupling, that is direct coupling, that usually we study in 13C NMR. 2J, it is two bond coupling, that is geminal coupling. It is in that case where different types of proton, that is A type and B type of protons, they are attached to the same carbon. Similarly, 3J, it is three bond coupling, that is vicinal coupling. It is common and usually we study about vicinal coupling. Now for 4J and 5J, it is long range coupling. Now we will take an example in which we will see the coupling or splitting of NMR signal. In this we have A types of proton and 3 B types of proton. For this A types of proton, their signals will be expected to come around approximate value of chemical shift, that is 5.5 ppm, and for B types of proton, their signal is expected to come around 1.9 ppm. The signals which is coming out of the B types of proton, it is more intense that of the A types of proton. It's because of 3 B types of proton and single A types of proton. These signals are expected without considering the interaction between A and B types of proton, but there is an interaction. So to understand about this interaction between these two protons, we need to first of all have a combination for the magnetic moment of the B types of proton, in which if all these 3 protons spin aligned to the direction to that of the magnetic field applied, then their magnetic moment will be having this combination. Likewise, if 2 protons are in the direction of the applied magnetic field, then it will give this possibility 2 are facing upward, first 2 are facing upward and last one is facing downward. Likewise, if first one is facing upward, then middle one will face downward and last one will face upward. At last 2 will be facing upward, that is to the direction of the applied magnetic field. Likewise, if first is facing downward, then this will give another possibility that 2 are facing upward. In this combination we have 3 possibility. Similarly, if 2 spins are facing downward, that is opposite to that of the applied magnetic field, then they are having this possibility, 2 is facing downward and 1 is facing upward. Likewise, 1 is facing upward, 2 are facing downward. Likewise, we will have a 3 possibility in this combination. And if all these 3 are facing to the opposite direction to that of the applied magnetic field, we will have a 4th combination. With this we have a 4 combination for the magnetic moment coming out of the B types of proton. So considering this, at first all these 3 magnetic moment which is facing towards the direction of the applied magnetic field, that is B naught, they will overlap with each other and the effective magnetic field coming out of this will be higher than that of the applied magnetic field for the A types of proton. So if effective magnetic field for the A types of proton is high, then the energy difference between the alpha and the beta spin state will be high for the A types of proton, so their chemical shift will be high. So if chemical shift will be high, then 5.5 is their chemical shift value, then the signal will expected to come more than that of the 5.5 ppm. Likewise, when two spins are facing, that is two magnetic moments are in the direction of the applied magnetic field, we have three possible combination which we have seen here already. So that gives us that two are facing upward and one is facing downward. So upward and downward, one will cancel out upward to that of the downward, but the one which is facing upward, it will be remaining. So due to all these three possibility, the resultant magnetic moment coming out of this combination will be towards the direction of the applied magnetic field. So the effective magnetic field will be greater than that of the applied magnetic field for the A types of proton. So if effective magnetic field is increasing, then the energy will be increasing for the alpha and the beta spin states of the A types of proton. So their chemical shift value will increase and their chemical shift will be coming more than that of the 5.5 ppm. And here the intensity of the signal is 3 times than that of the first one, is because here the possibility it is higher than that of the first one. So due to this higher possibility, here the signal's intensity is getting 3 times than that of the first one. So likewise, if we consider this combination in which one magnetization it is facing towards the direction of the applied magnetic field and two are facing downward, that is opposite to the direction of the magnetic field applied. So one facing upward will cancel with the one facing downward. So one facing downward will remain in each possibility. So with that, from this combination, the overall magnetization coming will be in the opposite direction to that of the applied magnetic field. So they will oppose each other. So due to that, the effective magnetic field will get decreased for the A types of proton. So due to that decrement in the effective magnetic field, here the energy difference between the alpha and the beta spin states will get decreased. So due to that, chemical shift will decrease, hence the signal will come before than that of the 5.5, that is the signal will come less than that of the 5.5 ppm. And here the signal intensity, due to this possibility more than that of the first one, here also signal will be 3 times than that of the first one. Likewise, at last combination, all magnetization they will be facing downward, that is all magnetization they will be facing in the opposite direction to that of the applied magnetic field. So due to that, the effective magnetic field coming out of this combination will be very very less. So if effective magnetic field is getting decreased, then the energy will decrease, which automatically results that the chemical shift will also decrease. So with that, we will get the chemical shift value, that is the signal will be less than that of the chemical shift value of 5.5 ppm. So the signal here intensity will be less than that of this, as possibility in this case is less. So with all these signals for A types of proton, if we combine all of them, we will get a quadrate signal like this with quadrate of multiplicity. And for B types of proton, here in this case, as we know, for A types of proton, the single proton is there, so the magnetization will be whether it is in the direction of the magnetic field and whether it will be in the, so there will be two possible combination for the magnetization of this A types of proton for interaction with the B types of proton, that is one which will be aligning with the externally applied magnetic field and one will be in the opposite direction to that of the applied magnetic field. So with that two combination of the magnetization from A types of proton, we will get a doublet signal for B types of proton. So likewise we will get the multiplicity, and talking about the coupling constant, their coupling constant will be the separation between these two peaks, that is what we have already studied. And here in this case their signal intensity will be 1:3:3:1 for the quadret multiplicity signal, and for doublet multiplicity signal we will have 1:1. That will be given by the Pascal's triangle, that is like this, in which it defines the binomial intensity of the signal for the protons. With that we will move forward to the coupling constant value for the protons, which will be at different positions. Like here in this case we have studied before about geminal coupling. So for geminal coupling, if the carbon is sp3 carbon, here the two protons of different environment which is attached to this sp3 carbon, so their coupling constant value will be ranging from 10 to 12 Hz. Likewise, if this is double bonded carbon having two different environment proton, that is A types of proton and B types of proton, then their coupling constant value will be two bond coupling, that is one bond two bond coupling will be 1.5 to 3.0 Hz. Likewise, we can move towards the vicinal coupling, where we can see if A and B are in cis position, then three bond coupling will be there, that will be around 10 to 12 Hz. And if A and B are in trans position, they will have three bond coupling, that will be around 16 to 18 Hz. With that we will move towards other important coupling, that is here in this case with the A and B we have three bond coupling, that is 1 2 3 bond coupling, 3 J A B 8 to 10 Hz. Along with that, at last we will see the aromatic protons, that is if A and B are in ortho position, then three bond coupling will be there, which will be around 7 to 8 Hz. Is very very important. And for coupling constant, if it is meta position, then four bond coupling will be there, that will be around 1.5 to 3 Hz. And that at last, if it is para, then five bond coupling will be there, that will be less than that of 1 Hz. With this we can consider some of the problems that are asked in the previous year examinations. Like here in this question, it is asked in the NET June 2018. Here a compound shows the following spectral data, that is proton NMR spectrum. They have given delta 7.9, doublet J is equals to 8 Hz, 2 hydrogen, 6.6, doublet J is equals to 8 Hz, 2 hydrogen. Similarly 4.3, quadret J is equals to 6 Hz for 2 hydrogen, 4.0 broad spectrum, 2 hydrogen, D2 exchangeable. And here 1.4, triplet J is equals to 6 Hz for 3 hydrogen. Without considering this mass data, we will first try to look the option to figure out the possible answer, in which we have the options given. Here it is para substitution, here also it is para substitution, here it is ortho substitution, it is meta substitution. With that we will look to the spectral data again. Here in aromatic region they have given 7.9, doublet J is equals to 8 Hz. So 8 Hz, it is ortho coupling with for 2 hydrogen. So 2 hydrogen they are giving the same signal. Here 6.6, doublet J is equals to 8 Hz, that is ortho coupling. And 2 hydrogen, it is giving the same signal. Likewise, so 2 hydrogen here, it is giving the same signal. Here also 2 hydrogen, it is giving the same signal. That means 4 hydrogens are there in the aromatic region, which are having the 2 of similar kind. So here 2 hydrogen, here they are of similar kind. Here also 2 hydrogen of same kind. Here if you see, this is also 2 hydrogen same kind. Here also 2 hydrogen of same kind. Likewise, if we see for the option number C, here all 4 protons are of the same, no, it is different kind. Here all 4 protons, here singlet signal will also come. So with that, option number A and B may be the possible answer, because in option number C and D there will be more than 2 signal for the proton in the aromatic region. Now if we go to the option number A and B, then we will have that for 4.3 quadrate J is equals to 6 Hz, 2 hydrogen. Now here 2 hydrogen is there, 6 Hz. So this 2 hydrogen will couple with this 3 hydrogen over here. So that will give a J is equals to 6 Hz, and it is quadrate multiplicity. Similarly, here also this 2 hydrogen will couple with this 3 hydrogen at coupling constant of 6 Hz, and it will give a quadrate signal. But this 4.3, it is highly deshielded proton. So deshielded, that means it is high chemical shift for 2 hydrogen over there. Here in this case, this lone pair of oxygen, it is involved in the conjugation with this carbonyl group. So this oxygen will deshield this proton more than that of this proton over here, because this oxygen lone pair, it is not in the conjugation with that of the carbonyl group like here in this case. So this signal is of these 2 protons over here. Similarly, this 1.4 triplet J is equals to 6 Hz, for 3 protons it is of this 3 protons over here, and for this 2 protons over here it is 4.0 broad spectrum for 2 hydrogen, that is acidic proton over here, that is D2O exchangeable. Likewise, we will get the option number A as a correct answer. Now we will move to the another question that is asked in the NET December 2019. Here we have an organic compound shows the following spectral data, that is proton NMR spectrum delta 1.9, 1.90 quintet 2 hydrogen, 2.18 triplet 2 hydrogen. Likewise, we have 4.0 broad spectrum for 2 hydrogen and 6.28 doublet J is equals to 8 Hz for 1 hydrogen, 6.35 singlet for 1 hydrogen, 6.48 doublet J is equals to 8 Hz for 1 hydrogen, 6.98 triplet J is equals to 8 Hz for 1 hydrogen. Here mass data is given. Now with the proton NMR spectrum, we will try to frame the structure of the compound. Here options are given. Here in this case it is meta substituted, here also it is meta substitution, here also it is meta substitution, here in this case it is ortho substitution. So if we see the protons over here, that is aromatic protons, here they have given that 6.35 singlet 1 hydrogen. So for this option over here, this proton will couple with this proton, and this proton will couple with these 2 protons. Similarly, this 1 proton will couple with this 2 proton over here, and here this proton will also couple. So there is no any possibility of getting singlet signal in this aromatic ring. So due to this data, option 4 will get eliminated. Likewise, if we move towards option 1, 2, 3, here if we observe carefully, then in this aromatic region we have 6.28, 6.35, 6.48, 6.98. So it is less than 6.5. That is, in this case, in this structure, this proton NMR spectrum data, the structure of the compound, they should have some electron donating group in the aromatic ring, so that their protons are getting, aromatic protons are getting shielded, so their chemical shifts are coming below 6.5, that is 6.28, 6.35, 6.48. Likewise, if we observe the figure carefully for 1, 2 and 3, because 4 is already cancelled, so in option number 1 it is electron withdrawing group. Similarly, option number 2 it is electron donating group. Now here we are up to our answer. Here also in option number 3 it is also electron withdrawing group. So these protons will get, orthoprotons will get deshielded than that of the metaproton. So with option number 3 and 1, option number 2 is the most appropriate answer according to the proton NMR spectrum given in the question. So with that we can assign the value for here 6.35 singlet for one hydrogen. If it is this proton over here, then yes, this can be this proton over here. And for 6.28 doublet, that is another ortho proton over here. And for metaproton it is 6.98, and for paraproton it is 6.48. So likewise we can assign the value, and option 2 will be the correct answer. With this questions in our hand, if you like my videos, don't forget to share it to your friends and giving thumbs up right down below. Thank you.